In this last lecture of the chapter, we're going to go beyond the hydrogen atom and we're going to look at the multi-electron atoms. We're going to examine the entire periodic table in a most general sense. We're not going to go into any details, but when you go beyond the hydrogen atom, you have to look at how these electrons in the same atom can interact with each other. Which orbital does each electron end up at? That sort of thing. And it turns out, as you know from chemistry, depending on where the last few electrons, the electrons with the highest energies, depending on where they end up, which orbitals they end up, the electrons can have very different behavior, and that can bring very different chemical properties to the element in question. So different elements, when combined together, can form all sorts of chemical compounds. So chemistry is a colorful science. But what makes chemistry such a colorful science? From quantum physics point of view, it is this following famous principle. No two electrons in the same atom may share the exact same quantum state. Many of you already know what this is. This is called the Pauli exclusion principle, sometimes simply called the Pauli principle or the exclusion principle. What exactly does it mean? It means that if we label the electronic state of each electron inside an atom with a set of quantum numbers, which we already did in the previous lectures. This is the principal quantum number, orbital quantum number. There's the z component of the orbital quantum number, and here's the z component of the spin quantum number for the electron, and so on. Suppose we use a set of quantum numbers to describe the state of an electron, then each electron must have a unique combination of these numbers. You cannot have two electrons in the same atom for which these numbers are identical. Okay? For example, if one electron already has 1, 0, 0, and 1/2, you cannot have another an electron have 1, 0, 0, and 1/2, because it violates the so-called the Pauli principle. Why do I say that it is the Pauli principle that makes chemistry such a colorful science? Well, we can take a look at what happens if we have a bunch of electrons. They need to satisfy the Pauli principle. If I have a bunch of electrons, where do I put these electrons in that atom? Well, electrons certainly want to go to the lowest possible energy, and so the first electron will go to the lowest possible energy level. That's typically what we label as 1s, and it may have a spin up. So ms is positive 1/2. If you have a second electron, then that electron want to occupy the same orbital, but it cannot have the same exact quantum number. Therefore, being in the same orbital, n, l, and m, these are all the same, but it has to have a spin down. That is the only quantum number that is different between these two pair of electrons. One spin up, the other spin down. And if you have a third electron, this electron is forced to go up because these two electrons already occupy the entire level. So the third one has to go up. And if you have a fourth one, it can still stay here, but it must have a spin down, and so on. You can keep on going like this. You can keep on going like this until the last electron is filled. And wherever it ends up at a certain orbital. That will dictate the chemical property of this element, because if this orbital is loosely bound to the atom, then that means this electron can easily escape from this atom upon meeting another atom undergoing a chemical reaction, which means this is probably a metal because it's more likely to lose that electron. On the other hand, if this is tightly bound, then it is less likely to escape. Rather, it's more likely to pull another electron in, and so on. So that becomes a non-metal. So clearly, the Pauli exclusion principle, along with the principle to minimize the energy of the atom, will dictate how you position these electrons. And the last few electrons, such as this one here, these are called valence electrons, because these are the electrons that will undergo orbital change upon meeting another atom, which means there's a chemical reaction going on. In a chemical reaction, basically what we have is we have two or more atoms or molecules. When they get close by, the valence electrons from each atom may undergo some change. They may go change orbitals or even go to a different atom. And this chemical reaction is aimed at lowering the energy of the entire system. And the behavior of these valence electrons will dictate the chemical behavior of this element. And that in turn depends on where this valence electron ends up. Is it in this orbital or that orbital? They behave very differently. So therefore, you have different chemical properties for different elements. But if there were no Pauli principle, in other words, two electrons or even more electrons can share the exact same quantum state, then what do you think is going to happen? Well, again, the atom wants to lower its energy as much as it can, so the first electron will come in, it will stay here. And the next electron says, there's nothing wrong with me staying here as well, so it wants to stay here as well. And even the next one says, I want to stay here, then I want to stay here. Of course, eventually when these electrons get too close, they're going to start to repel each other with quite a significant amount of force, Coulomb force, and then some electron may decide to go somewhere else. But you know, at least we can say you're not restricted to having only two electrons, one spin up, one spin down in the same orbital. If that orbital has significantly less energy than the next one, then you can have a whole bunch of electrons. And in the worst case possible, all electrons in the same atom, no matter how many electrons we have, will end up in the 1s orbital. But if that's the case, then what's the difference to have 20 electrons here and 21 electrons there? There's no difference, right? So chemically, there will be no distinction between different elements with different number of electrons or different atomic number Z. It doesn't matter what Z is. Then there will be no science called chemistry, at least not as we know it. Chemistry would no longer be a colorful science. You will no longer see millions and millions of different compounds all behaving differently in chemical properties. So therefore, we say the Pauli principle is what makes chemistry a colorful science. And many of you probably heard this term, the Pauli principle, first from a chemistry class. Without it, of course, we cannot even begin the science of chemistry. But in quantum mechanics, let's ask this question. Where does the Pauli principle come from? Can you argue? Can you reason behind it, find a reason behind it? Let's see. In quantum physics, the Pauli principle stems from the consideration of symmetry or anti-symmetry of wave functions involving the exchange of identical particles. You say, gee, what do you mean by that? Well, let's see here. What is identical particle? When I have two electrons, they're considered identical particles because they're the same type, okay, or two protons. They're also called identical particles. And one proton and one electron, these are not identical particles. So we understand that, right? There is such a thing in classical physics as well. So basically the same type. But how do they behave? How do identical particles behave? There is a little bit of difference, subtle difference between classical and quantum case. In the case of classical physics, even if we deal with two identical particles, say two electrons, let's see here. I have two electrons, one here and one there. Now each electron in classical physics, it has a well-defined velocity and a well-defined location at any given moment, because there's no uncertainty principle. I can, in principle, trace that particle, trace that electron. I know exactly where it is. And this guy also knows exactly where it is. Okay? So let's say this one and that one, they exchanged their position. So the green electron went here and the red electron went there. If you had a powerful microscope and you ignore all quantum nature of the system, you don't worry about the uncertainty principle, then you can, in theory, you can trace this particle from here to there and trace that particle from here to there and say, hey, I know something happened. The green one is now here, the red one is there. You can actually label each particle by knowing where it is to begin with, and you follow that particle. It never leaves your sight, no matter how small it is, right? You can trace where it is. So you say, this is the red particle. I know it. I will never lose sight of it. So it remains red. And this one remains green, and so on. You can label these particles. So they are different particles, even if they belong to the same type. They're both electrons. You can say, here's a red electron, here's a green electron. Okay. Now, in quantum physics, the situation is a little bit more murky because the electrons are better described by electron cloud. Basically, is the form of the wave function. You cannot exactly know where it is anymore. it sort of, it appears randomly within a certain region. It's called electron cloud. Outside the cloud, the chance of finding this particle is extremely small, so we ignore it. But within the electron cloud, it can be everywhere. But suppose these two electrons are still far away from each other. Say this belongs to one atom, here this belongs to another atom, so their electron clouds do not overlap. Okay, their electron clouds do not overlap. Then I can still sort of trace these electrons, even in quantum case, because this electron cloud, if it moves this way, that electron cloud moves that way. I know the electron is not exactly traceable, but at least I know it's within this region, right? If this entire region moves over here, this entire region moves over there, it's kind of fuzzy inside, but I know it's somewhere inside, okay? So I can still trace these particles, so they can still be labeled. Okay, this guy initially was here, this guy initially was there, and now I can follow them. This guy moves here, this guy moves there. So in this case, I may still be able to distinguish them because they are pretty far from each other, no overlap of electron cloud. However, things get more interesting as we deal with electrons that are close by, say two electrons in the same atom. And their electron clouds overlap. Okay, so we have this fuzzy ball of a probability. Within that, I know there are two electrons. But which electron is where? I cannot tell, because each electron can randomly appear anywhere inside this cloud. And suppose this electron went here, that electron went there, I would have no knowledge. All I know is the electrons are somewhere inside this fuzzy ball of probability. So when these two electrons made an exchange, so the green went to here, red went to there, there's no way for me to know, is there? And then we say, even if the electrons change position, I wouldn't know. These electrons cannot be labeled because they cannot be traced. I don't know whether the green one turned into red, the red one turned into green. I have no idea of following them. I cannot do that, and therefore we say these two electrons cannot be labeled, or we say they are indistinguishable. So you see, this is due to the quantum nature of the system when the electron clouds overlap. So we know that when it comes to quantum identical particles, when the two probability clouds overlap, I must consider these two particles as indistinguishable. I cannot trace them. So when they exchange positions, I will not know any difference. This puts a restriction on how I can write the wave functions involving more than one particles, if these particles are identical, such as two electrons. I have particle 1 in state labeled alpha. Alpha can be really a collection of quantum numbers such as n, l, whatever. And I have another particle, identical particle. Particle number 2 is in a state called beta. Beta, again, is a collection of quantum numbers such as n, l, m, and so on. And they're identical particles. Now, if I do not consider the fact that they're indistinguishable, I still consider them as distinguishable. So here's a red electron, here's a green electron. I can follow them, so I will never mix them up. I know which one this is, which one that is. Then how would I write down the probability that particle 1 is in state alpha, and at the same time particle 2 is in state beta? Well, these two events each has a probability, right? This guy has a probability of being in state alpha, and that one has a probability of being in state beta. The wave function, which describes the probability amplitude for particle 1 in state alpha, is psi alpha for particle 1. And at the same time, the wave function describing this particle in state beta is psi beta for particle 2. So I simply multiply these two wave functions together. Therefore, the probability, overall probability for this guy to be in state 1, state alpha, and that guy in state beta would be the product of the two probabilities. That's, a principle of a probability theory. You just multiply the two probabilities together. So therefore, we say psi of 1, 2, if you consider both two particles in the same wave function. So this is a wave function describing two particles, not one anymore. That's a new one, right? Psi alpha 1 times psi beta 2. Okay? So when you take the modulus squared, you get basically P1 times P2, as expected. This is the classical way of combining the two probabilities up. Now, what if we exchanged the two particles? So now the green particle goes to state alpha, and the red particle goes to state beta. Then of course, I have to rewrite it, right? This becomes psi alpha 2 and psi beta 1, right? Because beta now receive state beta now is occupied by particle 1, not particle 2. And then the probability, the wave function will be different because you exchange 1 and 2. Is that reasonable? Is that reasonable? Well, classically, it is reasonable because something has happened, right? The red one went here, the green one went there. But in quantum mechanics, there is no way for me to tell that they have actually made an exchange. When I observe the situation, I would know no difference. What does that mean? It means that the probability density after the exchange of these two identical particles should be the same, because the exchange makes no difference to the observation. Therefore, psi12 and psi21, these two wave functions, they only differ by exchange, particles 1 and 2. These two wave functions, they can differ as long as that difference makes no change in my observation. What I can observe is not psi itself. I never said I can observe the wave function, but what I can observe is the probability density. This I can observe. I can observe this. And quantum mechanically, I require that they be the same. Because when you exchange these two particles within the same electronic cloud, I cannot tell any difference. So these two must be the same. This is the quantum requirement for the wave function describing two identical particles. So under exchange between these two particles, the probability density should remain the same. Again, this does not mean these two wave functions must equal to each other, but the modulus squared must. So therefore, the classical way of combining these two wave functions would no longer be true. In other words, psi12 cannot be written as simply psi alpha 1, psi beta 2, because upon exchange, this will become psi alpha 2 and psi beta 1, and you see in general, these two are not equal to each other, right? These are two different expressions, you see? Therefore, this is wrong. You cannot combine them like that. So how would I rewrite the wave function so that it satisfies this restriction stemming from quantum indistinguishability between these two identical particles? I cannot write it this way, and therefore I have to do something else. Okay, let me introduce an operator called the exchange operator between particles 1 and 2. So here I have an operator P12. It operates on this function, wave function psi12, and the function becomes psi21. So that's the meaning of the exchange operator. Now, what if I take that exchange operator and operate on this thing again? So basically, I'm applying this exchange operator twice on the same wave function 1, 2. Okay, here is the first time you apply it, it becomes 2, 1, and then there is next one. There is another operation, but basically this operator simply exchanges 1 and 2. So after another one, it becomes 1, 2 again, right? So therefore, if you apply this operator twice on the same wave function, the wave function returns to itself, and this tells you that if you operate this thing twice, you just get 1, right? Because psi12 again becomes psi12. So this operator squared has a simple value of 1. Any wave function psi12 must be an eigenfunction of this p12 squared, this operator p12 squared, and that eigenvalue is 1. And therefore, p12 itself must be plus or minus 1, because its squared value you get 1. So it's plus or minus 1. Okay, so that tells you that when you take this operation psi exchanging 1 and 2 on any wave function psi12, you either get a positive value 1 or negative value 1. If that is the case, then our condition is definitely satisfied, because psi12 squared is not equal to p12 of psi21 squared, right? Because that's the definition of p12. But p12 is plus or minus 1. See that? It's plus or minus 1. So you can work this out. This is when you work this squared in. That's p12 squared times psi squared. But p12 squared equals 1, because p12 equals plus or minus 1. And therefore, you see psi12 modulus squared equals psi21 modulus squared. That is our condition. Okay, so we learned that under exchange, the wave function, under the exchange of two identical particles, you must either keep the same wave function or you attach a negative sign to the wave function. These are the only two possibilities if you want to satisfy this. All right. That's what I wrote down here. When you take P12 operating on the wave function consisting of the behavior of two identical particles, particle 1 and particle 2, then this becomes psi21, right? Psi21 has to be either equal to positive psi12 or negative psi12, because P12 again has only two possible eigenvalues, positive 1 and negative 1. And if the exchange yields the wave function itself, so the wave function never changes, it is symmetrical under this exchange, we call it the corresponding particles involved are called bosons. Bosons. It's named after a physicist by the name of Bose. And the second case, when you exchange the two particles, you get a negative sign for the wave function. These are called anti-symmetrical cases. So the wave function is anti-symmetrical under exchange because of negative sign, and the particles that are described by this anti-symmetrical wave function are called fermions, and then they are named after Enrico Fermi, another very important physicist. So for symmetrical wave functions, okay, so we're looking at these two cases separately, symmetrical and anti-symmetrical. For symmetrical wave functions, how does one rewrite psi12 from psi alpha 1 times psi beta 2 so that it is guaranteed to be symmetrical? How should I do that? Well, it turns out it's not that hard to do. Here's how I do it. Okay, I have 1 over the square root of 2, and then psi alpha 1 psi beta 2 plus psi alpha 2 psi beta 1. Now look at what happens when I try to exchange particle 1 and 2. If you did that, then this first term becomes psi alpha 2 psi beta 1, and that is identical to the second term, right? And the second term becomes psi alpha 1 psi beta 2, which is identical to the first term. So upon exchange of particles 1 and 2, the first term becomes the second term, and the second term becomes the first term. The entire wave function never changes. So we use the label S here for symmetry. So that's a symmetrical wave function. And where does the square root of 2 come from? Very simple, because what that means is that this symmetrical wave function really is the superposition of these two possible states, this state and that state. And each state has a certain probability, but you take the amplitude squared plus this amplitude squared, you get 1, because the amplitude squared is the relative probability of finding the particle to be in this state. And that amplitude squared is the chance of finding the system to be in that state. The system can only be in either of these two states, and therefore amplitude 1 squared plus amplitude squared equals 1. Therefore, each amplitude is the square root of 1 over 2, so that the modulus squared sum up to 1. It's just a matter of normalization. I mean, it's just an overall constant. Okay, that's symmetrical. Now what about anti-symmetrical? For anti-symmetrical wave functions, when I exchange 1 and 2, I should get the same wave function with a negative sign in front of it, right? How do I achieve that? Very simple. All I have to do is to change this positive sign to a negative sign. That way, upon exchange, the first term becomes the second term becomes the first term. So you have just exchanged the order between these two terms, but don't forget there is a negative sign, and therefore, overall, upon exchange of the two particles, the wave function returns to itself with a negative sign in front of it. This is called anti-symmetrical, is label A for anti-symmetry. So this is the difference between symmetrical and anti-symmetrical wave functions. Those are for bosons, those are for fermions, two distinct classes of identical particles. And as you can see clearly, neither of these two wave functions, symmetrical and anti-symmetrical, agree with the classical prediction. The classical prediction is just a simple product of psi alpha 1 and psi beta 2, which does not satisfy either symmetry or anti-symmetry under exchange. So the classical way of combining the two states for the two particles must be replaced by either this one or that one, depending on whether the particles are bosons or fermions. Okay, we're going to worry about which particles are bosons and which particles are fermions a little bit later. But let's say, suppose we have a bunch of bosons and a bunch of fermions. What is a stark difference between these two types of particles? Well, we're going to look at what happens when the two states, alpha and beta, are really the same state. Okay? It turns out when alpha and beta are the same state, the bosons and the fermions will behave extremely differently. Let's see. First of all, let's look at bosons. Bosons satisfy the symmetrical wave function, okay, when alpha equals beta. Okay, so basically two identical particles occupying this very same quantum state, alpha equal to beta. This is the symmetry wave function for bosons. Square root of 1 over square root of 2, psi alpha 1, psi beta 2, but beta is alpha, so this psi alpha 1, psi alpha 2. The same thing applies to the second term, psi alpha 2, psi alpha 1. Clearly, these are the two same quantum state. Okay, so we can combine them, and overall you get the square root of 2 times psi alpha 1, psi alpha 2. That is how the wave function of the symmetrical bosons reduce to when alpha and beta are the same at the same state. This is different from the case of classical. This seems classical. Classically, I ignore the symmetry or anti-symmetry. I just get psi alpha 1 times psi alpha 2 when alpha equals beta, right? Look at them. They are not the same, are they? They differ by a very subtle point, and that is the symmetrical wave function has a square root of 2 here. There's a square root of 2 here. So symmetrical wave function is square root of 2 times the classical wave function. You know what that means? When you take a squared, when you take the modulus squared, you get an extra 2 here, right? Extra 2 here. So if you consider the symmetrical nature of bosons, how does it differ from the classical prediction? If you ignore the symmetry of the wave function, you get an extra 2, which means bosons like to stay together. They like to congregate together. If the state already has one boson in it in fact would like to invite another boson there because the probability doubles. You see that? Okay? Compared with the classical case where the two bosons simply ignore each other. And so again, bosons like to attract each other. They like to congregate in the same quantum state. This does not mean the bosons have an attractive force between them, okay? I have never considered the force between the two bosons. In fact, I ignore the force between them. But just the fact that the wave function must be symmetrical for bosons means that two identical bosons like to occupy the same state because of this. Now, the more interesting case is for fermions. That's when the wave functions are anti-symmetrical. So psi A, remember, we have to get a negative sign upon exchange. So this is the most general case for the anti-symmetrical wave function. We already saw that before. But the difference here is that alpha and beta are the same. So I'm going to rewrite this beta as alpha and this beta as alpha. Now take a look. The first term is what? Psi alpha 1, psi alpha 2. The next one is also psi alpha 1, psi alpha 2, but there is a negative sign. The two terms then happen to cancel each other, and you got nothing. Okay? 0 if alpha equals beta. This is unbelievable, yet very simply true, which means if we're dealing with fermions, and the two fermions occupy the same quantum state, what is the resulting wave function? 0, which means it cannot happen. Wave function being 0, which means the state does not exist. Okay, so therefore, these two fermions, 1 and 2, if they're identical particles, they cannot possibly occupy the same quantum state because the combined wave function satisfying the anti-symmetry nature under exchange would be 0. They do not. Such a situation does not exist. This, in fact, is the origin of the Pauli exclusion principle. So now we know where the Pauli principle comes from. It is really because for certain type of particles, identical particles, their wave functions are anti-symmetrical under exchange, and therefore they cannot occupy the same quantum state, otherwise the wave function reduces to 0. Electrons satisfy the Pauli principle, as we know, so they are definitely fermions. Their wave functions must be anti-symmetrical under exchange. But what about other particles? Is there a general way to tell, for us to tell which particles are fermions, so they satisfy the Pauli principle, and which particles are bosons, they do not satisfy the Pauli principle? The answer is yes. This is so-called spin statistics theorem, first discovered by two physicists. One of them was the famous Wolfgang Pauli. Pauli finalized the spin statistics theorem, so it's generally attributed to him. What does it say? it says that there is an easy way to tell which particles are fermions satisfy the Pauli principle, which particles are bosons which do not satisfy the Pauli principle. All you have to do is look at their spins. Now we know there are spins is basically angular momentum, right? Intrinsic angular momentum. And angular momentum can have quantum numbers of integers like 1, 2, 3, 4. Orbital angular momentum for electrons certainly are integers, right? But the spin angular momentum we saw can have half integers, like electron has 1/2. In general, the spin angular momentum may be integers or half integers. These are the only two possibilities. And according to the Pauli spin statistics theorem, all half integer particles are fermions, half integer particles, and all integer spin particles are bosons. The most famous example of half integer spin particles are electrons. So electrons are fermions because they have half integer spin. The electron spin is 1/2, of course. Integer spin particles, there are many of them. Photons have an integer spin of h bar. The quantum number is 1, not 1/2. Helium-4 has 2 protons and 2 neutrons in the nucleus and 2 electrons outside. It is also a boson. It's a boson because protons, neutrons, all these are half integer particles. They're all fermions. But when you combine the 2 protons, 1/2 plus 1/2, the total angular momentum, spin angular momentum of 2-proton system becomes what? Becomes 1, and therefore it's an integer, and so we have what? We have a boson. Same thing for the 2 neutrons and for the 2 electrons. So helium-4 is a boson, but helium-3, the rare isotope of helium, is a fermion because we have we have 2 paired bosons. You have 2 paired fermions. These are the 2 protons, and that form a boson. But you have an unpaired neutron, which is a half-spin particle, so that alone can make it a fermion. So helium-3 and helium-4, one of them is a boson, the other is a fermion. They actually behave very differently, as we'll see later. Again, protons, electrons, neutrons, these are all half-integer particles. They're all fermions. And we cannot take these very lightly. These are extremely important in our understanding of the behavior of the entire natural world. For example, what if photons were half-integer particles and electrons were full integer particles? That means, contrary to the actual world, electrons would become bosons and photons would become fermions. Now, when electron becomes bosons, we know what happens, right? They wouldn't satisfy the Pauli principle anymore. Then all the chemical distinction between different elements would be erased. In a worst-case scenario, all electrons will go down to the 1s state. There's no difference in the chemical behavior of any element. You won't have metals, semiconductors. None of these things. They would just be the same. Okay, so the world will be totally just bland and just without any interest anymore. And what about photons being spin 1/2 particles? If that were the case, we would be in deep trouble too, because that would mean that they will have to satisfy the Pauli principle. So you cannot have a whole bunch of photons occupying the same quantum state, and that is not good, because in laser, for example, we'll see at the end of this chapter, you actually have many photons occupying the same quantum state. That wouldn't be possible if the photons satisfy the Pauli principle. So we cannot take these things for granted. If you exchange these simple spin quantum numbers from half integer to half integer to full integer, the world would be totally turned upside down, unrecognizable.